time that I've ever spoken in Phillips, so this is a lot of fun. My memory is that it was bigger. It's actually a much more intimate space than I remember. But it's pretty unlikely that I'm here. And there's a little story behind that. About 22, I wasn't even an X-ray astronomer, and 22 years ago, I'd applied, as everybody does. I was a postdoc in Europe, and I applied for, the usual 100 jobs, hoping one would come through. And it was around March, and I was sitting at Kitt Peak working with an old friend, Mike Wise, who's friends to many of you, and I got this email from Christine Jones, who, of course, I knew of but didn't know. And I was, at that time, married. I had a 2-year-old daughter. They had moved back to the States. I was about to take up a postdoc in Wisconsin, and I got this email asking about a job. Well, I had applied for a job and sort of wrote it off. My wife had said, well, what about Boston? Wasn't there a job there? And I said, well, they only hire good people. Most likely it'll come back with the postage returned, So anyway, I got this email, and I thought, well, I'm going to Wisconsin. And Mike Wise comes over and says, hey, man, you got to look at that. And so I said that to Christine, and she said, well, I said, I'm flying back to the Netherlands and packing up and going. And she said, well, can you stop in Boston along the way? And I said, well, what the hell? Okay, I'll stop in Boston. So, and then I get an email saying, well, would you give a talk while you're out here? And I said, well, I don't have anything, basically I don't even have any clean underwear. I'm ready to go back, and I don't have any way to give a talk. So I came and interviewed, and this was, at the fledgling Chandra Science Center. No, it was the AXAF Science Center. And at that time, there were 19 people, including secretaries and administrators on the job. And anyway, the choice was, they mentioned, well, I was there. They said, well, we'll get back to you in a week. And I said, no, I'm either, I got to know whether it's here, but I'm going to Wisconsin. And she said, okay. And then later on that day, Harvey actually offered me a job for the total of $41,600. And at the time, I thought I hit the jackpot. I had a 2-year-old kid. There was a pension with it. And anyway, to make a long story short, I was an optical astronomer doing polarimetry. And Christine took a chance, and here I am. I stayed for 7 years, and it's been 15 years, I guess, since I left. But anyway, it's great to be here. Most of you I recognize. There are many of you that that are new, so it's really wonderful to see you all here. So, and I should thank Christine, because if it weren't for her, I wouldn't be here at all. God knows what I'd be doing, driving a cab or something. So I'm going to talk about a couple of things. I come back every summer, and the person I've been working most closely with is Paul on a project that we've been working together for 15 years. And I want to talk about some of the new results that we've gotten. So the rough outline is I'm going to go through a very speedy intro. Because many of you know this stuff, some of these results, many of you are working on this, and so, and if you're not, you've heard about it from your colleagues. So I'm going to give a very speedy intro to get everybody up to speed, and I'm happy to answer questions at the end if I go too quickly. And I'm going to talk about feedback, which is a term that has, I think, is firmly established in the lexicon now in galaxy formation. I'll talk about the consequences of this thing called AGN feedback. I'll talk about new work that Paul and I were just working on this week, this scaling, feedback scaling with halo mass, which is work that we've done with my graduate student, Robert Main. And then for the remainder of the talk, I'll discuss new results on molecular gas and the cores of clusters, which is quite interesting and also very surprising. And these are my colleagues. I just want to, of course, Paul and several others, but I wanted to point out in particular the younger people, Helen Russell, who was a postdoc with me and is now back in Cambridge with Andy Fabian, Robert Main, much of whose work I'll talk about today, who was a master's thesis student with me and has now moved on to Toronto, and Adrian Vantium, another student of mine. So, what is the big picture overall? What are we trying to do? The question that we're trying to answer is basically this: why are all these galaxies red and dead? And 30 or 40 years ago, that would be a strange question, because certainly since the early 60s with the work of Egan, Lindenbell, and Sandage, the answer was relatively simple. What distinguished an elliptical galaxy from a spiral was largely angular momentum. Cold gas fell in, stars formed very rapidly early on. The ellipticals were low angular momentum systems, so the gas turned into stars very rapidly and left very little gas behind, whereas the spirals, which had more angular momentum, the gas fell into a disk and slowly churned its way over time into objects like the Milky Way. And then this was long before the notion of cold dark matter and the hierarchical structure formation ideas that we enjoy today. They're more than ideas, very good evidence on large scales that dark matter and dark energy drive the evolution of the universe, but that wasn't known in the 60s. So the question of why these galaxies are red and dead just seemed like an odd one then, but now it's right at the forefront. And what keeps them red and dead is a very interesting notion. And here, this is an early result. Christine Jones's that I think gave us, one of the answers to this, and that is, these galaxies, elliptical galaxies, are not devoid of gas, as we were told when I was a student. They have lots of gas, but it's just in a hot phase. So that gas is what's sitting around waiting to form stars, or would have formed stars, but hasn't. And the other angle on that is the cooling time of this gas is very short. That was something that Paul realized back in the 70s, Paul and Andy Fabian and Len Cowie and others. The gas had a short cooling time, should cool out and form stars, and it doesn't. And the answer that we've come up with now is that it's the black hole at the center that's doing this. And so that's the theme of what I'm going to discuss today. And so this notion that black holes keeps the gas hot is connected to this other idea called feedback, which is, the gas has to cool at some level to keep the black hole actives. The accreting black holes are actually the most powerful energy generators in the universe. It's a little bit of an irony, but it's true. And this energy is absorbed into the hot gas surrounding them and manages to keep it hot. And this notion, which goes back quite a long ways, Silk and Rees and others earlier than that discussed the concept of AGN feedback, but in the context of quasars. And so the discussion has changed over the last 15 years, and one of the biggest, one of the most important advances, of course, has come from the Chandra Observatory, which many of us have worked on. And so the idea is there are two types of feedback: the quasar mode, which primarily operated in the early universe through winds, radiation, and fast outflows. This drove out the cold gas that would otherwise form stars, fed the black hole, which grew into these monsters that sit at the centers of galaxies now that have masses of upward of 10 to the 9 solar masses, and regulated the formation of galaxies and presumably gave us this thing called the M-sigma relation. But since the earlier 2000s, it was realized that there was this other mode, which in the end may actually be, in fact has the best evidence for its existence, which is this thing called radiomechanical mode. And the idea is that radio jets, another form of AGN, I won't get into the different forms of AGN, but the upshot is that what determines the type of AGN, so we think, is just the nature of the accretion disk and the ratio of the black hole mass to the amount of matter falling in on it. And you can either get a quasar at high accretion rates or radiomechanical outflows at lower accretion rates. And these are the flows that we think heat up the hot gas, keep the gas hot, and in fact maintain galaxies red and dead. So it's a very different picture than what we had in the early 60s in the days of Egan, Lindenbell, and Sandage. And what are the two main pieces of, or the aggregate evidence, the fossil evidence that this in fact occurred, or at least that indicates that it's plausible, is this this notion on the left-hand side, or this plot on the left-hand side, which shows the luminosity function of galaxies. And I don't want to go into detail here, but I'm just going to give the upshot. The largest galaxies in the universe today, we expect, with very simple lambda CDM cosmogonies, we would expect that these galaxies should be much brighter and much bluer today. The biggest thing should be forming now. But they're not. Even despite the fact that there are many very large galaxies, they're red, they're largely dead, and they should be much more luminous and much bluer. And the idea is that feedback has suppressed the growth of these galaxies in a way that I'll describe in a few minutes at the high end, and at the low end it's stellar wind. So you have feedback essentially across the entire Hubble sequence, but it's just a different type of feedback, and it largely depends on the mass. And I'm going to touch on that quantity, mass, in this talk. And of course the other fossil evidence is the famous M sigma relation, which is a correlation between the mass, the supermassive black hole at the centers of galaxies, and the bulge mass. And it's a beautiful relationship, and what it implies is that every galaxy, or every galaxy sort of Milky Way and larger, has a massive black hole, and that nature formed galaxies in such a way that for every 700 or so atoms that went into star formation, one atom fell into the black hole. And when you think about that, that's a remarkable thing. It's done it with a very narrow scatter, and one of the quests in cosmology is to figure out how nature did that. There are many ideas, but one of them is feedback, as I'll describe here. And the first indications of this notion of AGN feedback, or at least the need for it, was the cooling flows. So these are what were thought to be sort of freakish systems in the centers of clusters that had very short cooling times. It was an area, it's been studied since the late 70s or early 80s. It was first noticed probably in Einstein images that the cooling time was very short at the centers of clusters, but something was either keeping it hot or the gas was cooling out. And it was a great puzzle. Often it was also a problem that wasn't very fashionable to work on, as Paul probably knows, and other people have gathered here. But it came to the fore once Chandra was launched, because Chandra, that it was a great problem. So the problem is that in the very centers of clusters, this is an X-ray map of I believe, it's not Coma, it's some cluster with a telephone number shown up there on the top. But what you see here is this cusp of emission, okay, which indicates very high density, short cooling time gas. And the scale here is quite large. The galaxy would sit right at the cusp there at the top, and down at the base here, this would be a diameter of about 200 kiloparsecs. And all of the gas in that region has a cooling time that's shorter than the Hubble time, and it should cool and form stars at the center. And of course, this picture on the right hand, famous picture by, on the right hand side, here's a famous picture by Andy Fabian showing that the gas does cool out, but it cools out at a very low rate, about a few percent of the integrated mass accretion rate that you would expect at the center, should fall into the center of the galaxies. So the question is, what's going on with that gas? And the answer that we seem to have converged on over the last decade or so is that it's the radio source at the center that's keeping this gas hot and preventing it from cooling. And I guess one question is, why did it take that long to figure it out? And there are a couple of things we didn't know. We didn't know quite how powerful radio sources were, because all we could do was measure the synchrotron photons from them. So we didn't know how much mechanical power was available, how much work was available to heat the gas. And we didn't know that their duty cycle is essentially on. I think now radio sources turn on and they essentially stay on. And so what is the evidence for that? Well, I want to show some of the pictures from the Chandra Observatory. These are three systems that we've observed. And what you can see in common with these are these big holes that are sitting in the X-ray emission. This is an object called MSO735 on the top left. This is all X-ray emission. Hydra A is a very famous radio source, one of the first ones we looked at with Chandra, and you can see that there are two bubbles in there. It turns out it has an enormous cavity system that goes beyond this that I won't discuss. But there are two cavities there, and then of course there's the famous Perseus cluster, which shows these cavities and all of these this X-ray emission here, or rather these little shock waves, weak shock waves or sound waves, as Andy calls them, an extra cavity up here, and so on. And when you superpose the radio emission, these just fill in beautifully. So this has been known for quite some time, and you can see that they have a variety of sizes. So in Perseus here, the size of these cavities is roughly 20 kiloparsecs, so it's sort of inside the galaxy. It fills the galaxy. These are galaxy scale ones up here as well. You can see the optical image shown here. It shows there's this big galaxy at the center. And then here's MS0735. These are sort of galaxy scales. This one is enormous. It's got a size of about 200 kiloparsecs across. This is the galaxy at the center. In blue is the X-ray. In red is a VLA image at about 300 megahertz, showing the radio source filling these cavities. And these cavities are enormous. They're a couple hundred kiloparsecs across, and the energies involved are also enormous. In this case, the energy is about 10 to the 62 ergs and change, and typically for these guys here, it's 10 to the 59 ergs, which is a lot of energy to be dumping into the intercluster medium. And clearly, by virtue of the fact that we see these things, it indicates that the work that's being done by the radio jets is displacing the gas and imparting its energy there. So how can we use these to do quantitative science? Well, the whole theoretical framework was developed largely by, I think, Paul and Eugene and others. Some of us helped, where the idea was that the cavities inflate, push against the surrounding pressure. They do work against the surrounding gas. And the other thing that we realized very early on was that these cavities were persistent. They didn't just collapse in a dynamical timescale, as you might expect. They actually persist and are able to rise in the gravitational potential well. So something had to be supporting them from the inside. And so their total enthalpy is somewhere between 2.5 and 4 PV per cavity. And it turns out that's a lot of energy. And we can use these cavities to measure not only the energy that's being output, but assuming that the dynamics are driven by buoyancy, which on a number of lines of argument is very close to being true, we can also get their ages. If you get the energy and the age, you can get the mean power. And that's something you can't get from a quasar. Okay, in a quasar, you only get the instantaneous power, but in these things, we get the energy and the time scale independently, so we can really study the evolution of these cavity systems to understand how the heating occurs. And when you work it out, we end up with energies in these systems that range between 10 to the 55 and over 10 to the 62 ergs. And by the time you're up to here, keep in mind that this exceeds the rest mass energy of a 10 to the 8th solar mass black hole. So that's a tremendous amount of energy that's being dumped in, by the way, a time scale of about 10 to the 8th years or less. So what this told us was not only is a lot of energy being pumped out, it's being pumped out in a fairly short and persistent time scale. And even though these things don't look like quasars, in many cases, they are at or exceed the total power output of quasars. And we simply didn't know that for 20 years because we didn't have this data. All we had were these radio sources, some of which were weak, some of which were powerful. And it turns out that even weak radio sources can be extraordinarily energetic and powerful. And I think this is one of the early diagrams that we made where we looked at a fairly large sample. This was largely from a student of mine named Laura Birjan. And we measured the jet cavity power, just as I described on the last slide, versus the radioluminosity and asked, how powerful are these things relative to their synchrotron power? And the answer is they're very powerful. So this is radio power versus cavity power, where this is unity, a ratio of unity, 10 to 1, 100 to 1, and 1,000 to 1. And what you see is, remarkably, these things are 100, sometimes 1,000 times more mechanically powerful than they are radio bright. Now, this wasn't a big surprise. It's been known since the 70s, very early on, that radio jets, the primary power coming out of radio jets was mechanical, okay, that they were radiatively inefficient. But we had no independent way of estimating that. And so what Chandra gave us for the first time was a way of estimating the ratio of their synchrotron power to mechanical power. And surprisingly, it turned out they were enormously powerful. And I remember when we started this project, I figured they'd all be down here, somewhere between 1 and 10, and that would be nice. But it was a big surprise to see some of these were just, essentially as powerful as quasars, but they were radio audible, but certainly not radio bright. And so what we did, many people did, is looked at the, the ratio of jet power, as I described a few minutes ago, to the cooling luminosity. And I won't go into the details of how we do this, but essentially what this is the amount of power coming out in this cusp that I showed a little while ago. And on this axis is the power as calculated as I described on the previous slide. And it shows the ratio. This is a ratio of unity between the two power outputs for 16 PV of work, 4 PV of work, and 1 PV of work from the cavities. And we assume 4 PV is the most likely because that assumes it's a relativistic gas filling it, and that's a reasonable assumption given that they're filled with radio emission. And what you can see is that for the most part, on average, the amount of power that's emerging from the centers of these clusters in the radio is comparable to the cooling power. So the jets can keep up. At least energy, the energetics works out. But what you can see is there's quite a bit of scatter here, and in some cases they lie below, other cases they lie above, and you'd expect to see that too, because as I'll show in a little while, there is cooling going on. There's a lot of gas in the centers of these. And of course, you need to have a lot of gas to fuel the AGN and keep this whole notion of a feedback loop going. The other thing to notice is that you see a trend here. Somehow, some way, the black hole, which of course sits down on a size scale that's of order of the solar system, knows about what's going on over these vast scales, okay, in the cluster. And you can see that here. The power output seems to be reasonably finely tuned to the power output of the black hole, which is on that axis, is finely tuned to the power output coming out of the atmosphere, which is shown over here. So big systems, those systems that need a lot of heating, have powerful radio sources, powerful cavities, and the giant ellipticals shown over here, which obviously are weaker. They have weaker cooling, persistent but weaker cooling. They also have commensurately lower power sources. So this is telling us that nature understands. There's a relationship between the black hole and the gas cooling on large scales, and it seems to be fine-tuned. So we see that experimentally. We don't understand how that fine-tuning occurs. So that's the intro. So that's where we are, and we've been studying feedback on several angles for some time. And the one area that I've been anxious to look at, and Paul had been anxious to look at, is how does this feedback scale with halo mass? And there's a lot of reasons why one would want to look at that. Not only to connect this stuff to simulations, but to try to connect it to things like the M-sigma relation, which again are related to mass. So what we did is a pilot study of 45 clusters. We drew from the high flux sample of Reitberg and Boehringer, and we added other systems that we had studied from the Chandra archive for their other cavity systems, some with and some without cavities. And we went off and measured their masses. Just as a check, we recover the mass temperature profiles from the literature, stuff from Vaklin, Markovich, Allen, and so on. We've successfully recovered the scaling relations that they find beyond the center, so we're reasonably confident that we're not screwing up too badly. And I just want to show you the upshot of one of the plots from this paper they're working on. So what I'm showing on the left-hand side here is cavity power calculated just as I described earlier, versus M2500. And what you can see here, this is calculated again both from the Chandra data, and what's plotted is the primary sample, which is just the high flux sample, and then the extended sample are all these other systems that we've added in to try to get better statistics. And what we find is this trend between the cavity power and M2500. It scales with a power line index to the 1.5. And we did it this way, to retain calibration contact, to at least try to control for systematic errors. And what we found is when we added these other systems in that weren't drawn from the high flux system, it didn't change the slope. So we're reasonably confident that this slope is pretty good, or at least as described up there, the accuracy as printed. And we also looked at gas mass, which is shown on the right-hand side, and we were not able to, it looks like the trend with total mass is slightly better, but statistically we can't differentiate between gas mass and halo mass, and both show a correlation with slightly different slopes. There is also a correlation with galaxy mass, and that's not surprising. We've known that the central galaxies correlate with the mass of the cluster, the temperature of the cluster, and also the gas mass, but the correlation is much weaker. So it doesn't look like the galaxy is really driving this. It's probably either the gas mass or the halo mass, or some combination. But very interestingly, the scaling that we get is consistent with the m-sigma relation, just making very simple assumptions about how things scale in the center. And when we were working on this, Paul said, well, look, let's check to see how this scaling compares if we just assume that it's being driven by feedback. And so a couple of hours of algebra, and Paul came back and compared his slope to what we find. And we find that the scaling that we get is just what you'd expect, or within 2 sigma of what you would expect if this scaling is driven by feedback. And so this is pretty exciting. I think what it implies that it's at least consistent with m sigma, and it is at least consistent with the notion that these things are balanced by cooling, and that the properties at the center are driven by feedback. But what we don't know is what the primary variable is. And so this is just a start. What we're going to do is continue on and try to build this sample up. There are a couple of hundred clusters in the sample, in the Chandra archive, and we're going to do as many as we can. But more importantly, these scalings here are important. This has some dependence on the gas mass fraction and other parameters. But the point is that scaling and the scaling with the black hole mass and feedback properties, are tied. They're sensitive to each other. So I think this is a promising avenue to try to look at this in a more general term, which is mass. And the other, there's a practical side to this. Most modelers build most models are mass-based. Okay, so they're Lambda CDM models model best the halo mass and not the baryonic component. And so tying this to halo mass could potentially be a nice, convenient way for modelers to take the scaling relations, and they can stick them in their codes, at least as a consistency check. And that avoids all of the assumptions, or many of the assumptions that people have to make, or generally make, about feedback, whether it's Bondi accretion, whether it's cold accretion, and so on. You can simply stick these in the code and see if you can reproduce nature that way. But it turns out there's another parameter. So it looks like feedback is closely tied to mass, but it turns out it's also closely tied to central cooling time. And I can show that evidence here. This is a bit of this plot is a little hard to read, so I'll take you through it. This is mechanical power again, as I described before, versus M2500, and the black dots are the objects in clusters that have a central gas cooling time less than 1 gigayear. And why did we pick that? This roughly corresponds to the time scale that we found earlier. We and others found corresponds to the cooling time where cooling instabilities are driving star formation in the centers of galaxy clusters, in the brightest cluster galaxies. The timescale we find is slightly less than that, but given the large range in redshift that well, not a terribly large range, but significantly large range in redshift. Some of these are out to 0.1 to almost 0.2. We needed to take the cooling time from a large enough volume so that we wouldn't be affected strongly by resolution effects. So we chose 1 gigayear, and we plotted up this relationship with systems with central cooling time shorter than a gigayear and longer than a gigayear. And of course, as you would expect, as I showed in the last plot, there's a trend in the systems that have a cooling time shorter than a gigayear, which is shown in the black dots, and the trend goes away in clusters that have cooling times longer than 1 gigayear. So, and there are other differences here. It turns out that the objects that are sitting, the CDs and radio sources that are sitting in clusters with short cooling times have radio powers that are on average roughly about 100 times as powerful as the objects in clusters outside of cooling flows. And we see this trend, and there's no trend in these. Now that doesn't mean that they're radio quiet, the ones without cooling flows. Something is obviously driving gas to the center in these and can drive very powerful radio sources. So you can see here these guys on top here. They're just as powerful as some of the systems that have short cooling times, but they don't participate in the trend. So what it's telling us is there's a lot of heating in these systems, whether or not they're driven by feedback. And we think that the black dots are driven by feedback and these other ones aren't. So they're heating their atmospheres, but they're not doing it in this tightly controlled feedback loop. So what this is telling us is that there are two factors. There are mass, so the halo mass and the central cooling time seem to be driving this feedback loop. And the interesting thing here also is that these are two things that in principle can be measured and measured in simulations, and these scalings can be put into simulations and tested to see if they can reproduce what we observe. So that's, there are other results as well, but time is moving on, and I wanted to get on to some of the newer results from ALMA. So I'm going to switch gears a little bit. Paul and I are just finishing that paper up. And I wanted to talk about our ALMA project. So, as you know, ALMA has been commissioned, or is being commissioned slowly, it seems, over the last decade. We've applied to observe several systems, and we were successful. We have about 6 clusters that we were successful at observing time. And the basic questions that we want to ask are, so let me step back. The centers of cooling flows have been known now for about 15 years, primarily through the work of Alistair Edge, to be rich in molecular gas. It's a little bit surprising, but there are many of these systems that have molecular gas masses exceeding 10 to the 10. They have star formation rates that are many tens to, in some cases, several hundreds of solar masses per year. And the champion right now is the Phoenix cluster, which Mike McDonald has worked on, which has a star formation rate of, I think his last calculation was 800 solar masses per year. They're rare, but they're out there. They're rare in numbers. Compared to the total number of galaxy clusters, they're rare, but there are lots of them because there are lots of galaxy clusters, of course. And these things have gas masses that are anywhere from 10 to the 9 to 10 to the 10 solar masses of molecular gas. Now that's a lot of molecular gas. The Milky Way has about 10 to the 9, so it's a chunky L-star galaxy, and it has about 10 to the 9 solar masses of molecular gas. These things, in many cases, exceed the Milky Way by factors of 10 to 100. And the question is, where's the gas coming from? We think it's probably cooling out of the atmospheres, but also what is the gas doing down at the center? Does it look just like a normal ULERG or a normal spiral galaxy? Is it in disks? And then ultimately, what role does this gas play in the feedback loop? So these are some of the questions that we've asked. It's very hard to answer questions when this many questions when you only have 5 or 6 objects, but we'll take that. It's been slow going with ALMA. It's taken a long time for them to commission the data. It seems the time scale from getting your proposal accepted, if it works out, to getting the data can be years. But in any case, I can show you some of the results that we've gotten thus far. So we picked objects preferentially, obviously, that had a lot of gas in them. So this is a very biased sample. But you don't want to go to a new telescope and point at things that don't have much molecular gas. You want to get a signal. And so we picked these. The granddaddy is Abell 1835, which has about 5 times 10 to the 10 solar masses of molecular gas. and that's assuming the galactic conversion between CO and H2. And Abell 1664, which has about 5 times 10 to the 9 solar masses of gas. Both of these objects are forming stars at a rapid rate. Abell 1835 at about 200 solar masses per year. And to compare that, our galaxy is forming stars at about 5 solar masses per year, and it's considered to be a burgeoning galaxy. So these things are very unusual for elliptical galaxies, but they're out there at the centers of clusters, and all of them lie at the centers of clusters that have cooling times that are very short, much less than a gigayear, and generally about 500 million years. Okay, so they're burgeoning. MS0735 or Parkes 0745 is also, similar in that vein. It's got about 5 times 10 to the 9 solar masses of molecular gas, and we've gotten ALMA data to look at these. There are several others. Mike McDonald got the Phoenix cluster, and that's a beautiful observation. Grant Tremblay as well has data on Abell 2597. So we're slowly building up this sample, and just, to tell you just a few years ago what we had to deal with, this is from Alistair Edge's pioneering work discovering these things. He's found CO in about 50 of these now. But that was Abell 1835's discovery spectrum. That's the granddaddy. That has more molecular gas than any of the ones we know. That's the discovery spectrum. And that's sort of what an image would look like just a few years back. So what would you conclude? There's a lot of gas. It's centrally concentrated. It probably looks like any other ULIRG and so on. But we had some surprises. So keep that in mind on the left side. This is what ALMA gave us in just a little over an hour of integration. So this shows the Abell 1835 CO1 to 0 emission line, and it's beautiful. I mean, you look at the baselines. They're just marvelous. And this is the CO3 to 2. I'm sorry, the CO1 to 0 on Parkes 0745 as well. And again, you can see it's got very nice baselines. What was our strategy? I should have mentioned that in the last slide, just to clarify this. You see two. What we did is we went out and got 1 to 0 to look at the larger scale molecular gas, and also to get a pretty good measurement of the mass to compare to earlier observations. And then we got also CO3 to 2 observations, and that gave us much higher resolution that allowed us to look right into the center and search for disks and other structures associated with the radio jets and so on. So the 1 to 0 was more for total gas mass, and the 3 to 2 was to do the morphology right in the center. And I'll show you images of both of those. But the first thing that struck us when we looked at these spectra was how narrow they were. Okay, so this is gas that presumably is falling in, and you don't have to fall very far to get to very high speeds at the center of a cluster, first of all. And secondly, they're sitting in the biggest galaxies in the universe. Okay, they have typical stellar velocity dispersions of 250 to upward of 350 kilometers a second. So that's what we expected. And generally, gas sitting in disks, for example, it's been sitting around for a long time. It could sit around for as much as 1 billion years. We would expect that this gas would have gotten to know its host gravitationally, and apparently it hasn't. These are very narrow. Okay, this one is roughly 120 kilometers a second wide. Okay, it's a big puzzle. Immediately it struck us. And this is the CO3 to 2 image of the center of Abell 1835. And what you can see is the gas in this one is very much centrally condensed. The gas densities are not quite as high as you get in a ULIRG, but half of the gas is unresolved. It's in this center block. So on the left-hand side, this shows the overall image, and that block corresponds to this grid of spectra. And the first thing you see is these spectra are very narrow. Okay, and their systematic velocities vary very little. Okay, so the velocity, so this gas cannot be in virial equilibrium with the stars if it's traveling around on random orbits. But what we thought was, maybe we just got lucky or unlucky, and nature gave us a disk that is nearly face on. Okay, it was the only, and so that this gas is supported gravitationally, but it's supported in a disk. So what we're seeing here are the velocities in and out of the disk. Okay, it made a lot of sense. Wrote a paper on it. It all hung together. But, you know, in the back of our minds, we knew that we only get one shot at the wheel. This is the only time we get. You know, it's very unlikely to find a disk that is essentially face-on. And if you work out the numbers, it has to be face-on to a few degrees, which is pretty unlikely. So this was one shot at the wheel. And we interpreted it as Norm Murray had a big hand in this, Norm and Paul, at interpreting this as a face-on disk where we're seeing gas velocities in and out. But even then, these gas velocities are quite high, so the disk has to be puffed up. That might be fine, because with the star formation of 200 solar masses per year, a lot of energy is being pumped into that gas. So that was it. It sounded great. I thought it was a pretty compelling argument. There's a lot of gas in here. It's fueling star formation at a very high rate. There's also these little arms up here that extend up. It turns out there are X-ray cavities sitting out here, and it looks like maybe this stuff got drawn up. But there's a further story on that as well. This shows the same image with this X-ray image. This is a 200 kilosecond Chandra image of the center of the galaxy cluster. Remember, there's a big galaxy sitting at the center here, forming stars at 200 solar masses per year, and there's a couple of cavities here. They don't look very interesting compared to the nice ones I showed at the beginning, but this is a very high pressure, distant cluster, and it turns out that the power in this thing is over 10 to the 45 ergs per second. This is pumping out energy, you know, as vast as a quasar, but it's one of the most radio quiet systems that we know. So it's very inefficient. It's radiatively inefficient, but it's pumping out a lot of power. And it turns out that there's some structure coming up. It's pretty dicey that may indicate that this stuff is interacting with the bubbles that are rising up. But the real evidence comes from dynamically. So what's shown here again are these very narrow, velocity profiles, which turned out to be our best friend in this case, because we would not have seen this enormous flow of gas had the velocities not been narrow. Okay, so what's shown up here is this CO 1 to 0 image, and there are two boxes shown here, and those boxes correspond to these spectra. And so just to remind you, there's 5 times 10 to the 10 solar masses of molecular gas. And in these extended regions, what we found is that there are these wings. There's a blue wing here, which corresponds to the gas just north to northwest of the nucleus. And then there's this red wing over here, which corresponds to this gas to the southeast. And they both point in the direction of the bubbles. It might be a coincidence, it might not be, we don't know. But it turns out when you integrate the mass up in that, it's 10 to the 10 solar masses of gas. Okay, and it's moving along that direction, or that direction, and that direction at speeds of between 200 and 450 kilometers a second. So it's moving, I think, it's moving at speed, but there's not enough speed in there for the stuff to leave the system, most likely. Okay, so it's probably, it looks like it's either coming in or going out, but if it's going out, it's probably not going to leave. It's probably going to come back eventually. So the question is it coming in or going out? And at face value, you don't know, because it's an emission, so you don't know where it is on either side of the galaxy. But what we reasoned was that it's very unlikely to be coming in, simply because we don't see high velocity gas in the nucleus. Okay, if the stuff is falling in, say cooling out of a cloud and falling in, you expect the highest speed stuff to be sitting down in the nucleus. Okay, and we don't see that. If you look in the center, it's completely devoid of high velocity gas. So it's possible that the stuff is falling in, but that would mean it's very transient. Okay, it just started to fall in, and we just caught this at the right time. So what we argued was that most likely this stuff is actually going out. It looks more or less like gun barrel acceleration, and it's been drawn out either behind the cavities or drawn out from the center, with the cavities. The problem is, how do you do that? There's an enormous amount of energy in the cavities. The kinetic energy of this gas is only 1% or 2% of the energy of the cavities. But it turns out that the mass involved in this thing is about a quarter of the mass displaced by the cavities. So it's very hard to imagine connecting this stuff up with the cavities and drawing it out. I mean, this is, as my postdoc Helen Russell said, you know, it's like trying to move a boulder with a hairdryer. Okay, so it's very hard to move these. I was originally saying fire hose, and she said, no, it's a hairdryer, and she was right. So anyway, how do you do that? We don't know. One of the ideas is that maybe the bubbles are drawing matter out, warm stuff that's about a keV or below, and it's cooling out along the way. So it's essentially enhancing cooling as the bubbles fly out. So it pulls stuff out, the warmer gas from the center. And the time scale to draw this stuff out, it turns out, is comparable to the cooling time scale for gas that's a little bit below a keV with roughly solar abundances. So maybe that's what's happening. But the interesting thing here is it looks like the jets somehow are interacting with the molecular gas. And we started this project, I said, no way. You know, the density contrasts are 10 to the 5. The molecular gas is ballistic. It's going to be in disks. And the jets won't be interacting with it. And it's just fun to be wrong about this stuff. So one of the other systems, and I'll get back to the notion of a disk. One of the other systems we looked at is Abell 1664. Again, this is an HST image showing the center of the galaxy. All of these knots are star formation forming at a rate of about 20 solar masses per year. There's a big dust lane here. And when we looked at this, we found that the gas was in two velocity systems. There's what we would call a high velocity system at minus 580 kilometers a second, shown over here, off the center of the nucleus, not really associated with any star formation. The star formation seems to be away from the molecular gas. And then there's one at the systemic velocity right here, sort of in two lumps. And you might convince yourself that it's disky, but it turns out that the center of mass of this disk is would be, if it were a disk, offset from the center of the galaxy, which is kind of weird. And also the gas isn't sitting at the locations where we see star formation occurring most rapidly. You might convince yourself that this is a disk or a nascent disk. I'm not convinced. It just doesn't look like a disk to me. It looks like this stuff, it may have some shearing motions, but it very much looks transient, whereas the star formation is over here. So in this case, the molecular gas, it's not in a disk, and it doesn't seem to be tracing the star formation. What it does seem to trace is dust. This is dusty gas, but it's just not doing what you might expect it to do. It's also at high velocities. We don't understand the origin of the high velocity. This one doesn't have obvious cavities or radio structures that would indicate it pulled it out. We did get a deep Chandra observation of this thing that should arrive soon to look more carefully at that. But it's just not clear where these velocities are coming from. Now, mind you, velocities of this magnitude can easily be accommodated dynamically if the gas is cooling out of clouds at a very modest distance, falling in from 15 to 20 kiloparsecs. The gas would easily accelerate to these speeds. So maybe that's the answer in this case. That gas is moving at speed. It may have nothing to do with the radio source. It may have something to do with it. We simply can't say. But then we got another one which surprised us as well. This is Parkes 0745. We see the total gas mass found by Alistair was about 5 times 10 to the 9 solar masses, and we've recovered that with the ALMA data. But again, the morphology is just very weird. Okay, this X marks the center of the galaxy. That's where the nucleus is. There's 5 times 10 to the 9 solar masses of gas, 5 times that in the Milky Way. Okay, this stuff did not come in from a merger. There's just too much gas to accommodate this stuff coming in from, say, a spiral galaxy crashing into the center. But it's not even sitting at the center. It's sitting off to the side here. Okay, there's about 2 10 to the 9 solar masses sitting over here, about 10 to the 9 solar masses here, and then in this filament trailing up there, it's about about the same, about 1.5 times 10 to the 9 solar masses. And this guy is forming stars at 10 to the 20 solar masses per year, so a very healthy rate for an elliptical galaxy. This black spot here, which is optical emission from Hubble, shows us where the star formation is occurring, and this is where most of the gas is. And as I'll show on the next slide, it's not sitting in a disk. Okay, So it's forming stars at a rapid rate, but this is not the stuff, it would seem, that the stars are forming out of. Now, what is the origin of these filaments? Who knows? There are two very large cavities, which I'll show on the next slide, sitting up and away from this. And if you use your imagination, I'm going to skip a slide here. If you use your imagination, you might think that these filaments here, that one and that one, may have been drawn up so this box indicates that image. So you can see, ALMA is looking way, way down into the centers of these clusters. This is the Chandra image. There's a cavity here, and there's a very large one up here that are moving, in some direction through the cluster. And you might imagine that this stuff was disrupted by the AGN outburst that occurred, 10 to the 8th years ago and pulled it up. Maybe that's what's happening, or maybe the stuff is cooling out behind it and falling in. But here's the part that really makes this whole scenario hard to understand. This is the velocities. By the way, we couldn't do this stuff 5 years ago. I mean, the quality of data that slow as the data is coming and hard as it is to get, the quality that we're getting from ALMA is just amazing. But this shows the velocities. And again, it's bizarre, okay? The velocities that we're seeing are tiny, okay? So they're 100 kilometers a second. This is 100 kilometers a second, 150 kilometers a second. All of this stuff, this green stuff, that's 50 kilometers a second. It's slow, okay? These are massive galaxies. These are big clusters. And this stuff is, it's just not moving. It's not responding to gravity, okay? Same thing with the velocity dispersion. It's way below what you'd expect if this stuff had gotten to know, the galaxy. And so we're coming up with the results that are very much consistent with what Larry found in NGC 5044. These things are probably transient. Even though there's that much gas, I mean, this is a lot of gas, but it seems to be transient. It's not in dynamical equilibrium, but at the same time, stars are forming in these systems. And they're forming it at an enormous rate compared to, say, just a normal spiral galaxy, and the amount of molecular gas there is high. So what we thought we would get is something like Eulerge, just, piles of gas at the center and disks, everything would fit. We do, the Schmidt-Kennicott relation and wave the flag and go home. And to be honest with you, I don't have any idea what's going on, and I keep hitting Paul with this, and he doesn't have any idea. And so, I don't know what to tell you, but it's very exciting. It's a lot of fun, and it keeps us off the streets. So that's it. What I'll do is I'll just leave my conclusions there and take questions. Thanks very much for having me. On the plots that I showed, there are no spirals. So these are all giant ellipticals to CD galaxies. Okay, and the situation between ellipticals and spirals may be very different. I mean, feedback is thought to occur in both systems, but feedback in spirals is most likely dominated by, so we think, at least for the disk component, by supernovae, so the stars. It may be that in the early moments of the formation of spirals, feedback from the black holes at the center were important at, say, regulating star formation in the bulges, but we don't know that. It's hard to imagine, for one thing, spirals typically are not powerful AGN, as our own galaxy, has demonstrated, and most others are not powerful AGN. And even if they were, it's hard to imagine how you would couple the energy emerging, to gas sitting in a disk. So that's a long-winded way of saying I don't know how they participate. Although if you look at the plot that I showed, the general idea is that it's stellar feedback that governs ellipticals and and irregulars and so on, and that it's AGN feedback that govern the most massive galaxies, which tend to be the ellipticals and CDs.
Right. I just wanted to point out that it should be pretty well understood that you can't tell the location of star formation from optical images, right? Because the CO is itself obscuring the star formation, right?
Yeah, that's a worry, and I guess so. So the way to check that is these also have far infrared emission. Okay, and if there was a lot of absorption, and there's bound to be some absorption, but if it was a huge effect, what you'd expect are highly discrepant star formation rates between the UV, which was what I was showing, and far infrared. So you'd expect, all of this reprocessed UV to be coming out in the infrared, and you'd expect to get much higher star formation rates. And generally, when you compare the UV and the far infrared star formation rates, they're consistent with each other within a factor of 2 or so. So whereas obscuration is probably important, I don't think it's, at least all indications are that it's not a huge effect in these systems, not as much as you would get in other sort of buried AGN and galaxies in the early universe.
On the first part of your talk, you placed a lot of emphasis on halo mass, and more emphasis that I'm comfortable with. And the reason being because in simulation we see that at a fixed halo mass we have a diversity of merger histories, concentration, formation times, and relaxation stages. Have you considered looking into those variables, say at a fixed halo mass, if you have different richness or different concentration?
Yeah, we calculated things like concentration parameters and so on, but we're just getting started on this, so we have not gotten into that kind of detail when looking at that. This is an ongoing project, and we will look at stuff like that. But with 45 objects, we're just trying to feel our way in, and we were surprised to see that we got a correlation at all. In fact, we started out with just temperatures and noticed a rough correlation. So we're not there yet, but we're getting there. And I will step back and say we don't know what the primary variable is. It does correlate with halo mass. That may be a secondary correlation. The point there is that it's still a very useful correlation from the point of view of modelers and so on. And it's something that we just need to figure out. I don't understand it either.
Well, it's more of a remark. I've looked at a lot of galaxies in the and I don't find these ALMA pictures terribly upsetting. I think most galaxies, the centers are asymmetric, and they're big blobs on one side and not on the other side. It happens all the time. So, I don't know. My one suggestion might be the 21 centimeter high-resolution maps with the, say, BLA might be a way to really figure out what's going on with the CO and the interaction between the CO and the cavity. If only we could do it. So long ago, several of us, including me, attempted to detect these things in H1, and it turns out that these things are H1 poor. The amount of mass in CO vastly exceeds the amount of mass in H1. It's the flip opposite of what you see in a normal spiral. So if we could do these with H1, we would have done it long ago, and maybe it's time now that the EVLA is super powered, it's time to go back and try to do it. But these are H1 poor. And and of course there is a trend that as you go to earlier and earlier type galaxies, the ratio of CO to H1 increases. Okay, so it's not like the Milky Way where it's the flip opposite. These are very different. These are molecular gas rich, and there's almost no H1. Only Perseus has been detected in emission with H1, and that's sort of in the few 10 to the 9 range. And the other ones that have been detected in absorption. And so we have no way to get the mass. So you should do carbon 2 at ALMA.
It's a great idea, but man, we're just getting these was like pulling teeth out of a crocodile. So we're trying.
All right, if there are no other questions, let's why are you saying that the jets don't connect?
I didn't say they don't.
Because the
there's interact and interact. I mean, there's running into. The thing is, it's like running into a brick wall.
Right, that's a different story. But you have the correlations between the velocity change in the molecular gas and in the jet structures. And it is what Rafaela shows,
Yes.
Pat Hunter is showing, these all the results. This is within the galaxies, of course.
You mean the paper she just published?
Well, that's one, but there is, 10 years of
No, she did mainly the H1 stuff,
Yeah.
and I agree. But the H1 could be much thinner. The CO is the very high density stuff. It's like running into a boulder. It's much more. It's much higher density than the H1. The H1 is sort of the fluff.
all right.
I'm wrong though. It's clearly happening, so I'm happy to concede. I just didn't expect it.
It's actually interesting because when you see this very powerful young jets, to see the interactions of this, I think they have one to look at.
Bicknell stuff. Bicknell stuff is what really turned my head. It's like, wait a minute, you got to
so the
rethink this.
simulations, yes, and everything. Yeah.
But he was doing very narrow jets that were quasar objects. Very powerful.
Yeah, so this is what these young sources are. Very powerful.
I know.
No, it's good.
Touche. I'm
Very good, very nice
I stand
results.
corrected. I'm excited. Being wrong is more fun
No,
than
it's
being right.
exciting results. My question was how much mass was in this CO, which you were showing.
Well, I think I mentioned that. It's 10 to the 10.
10 to the 10, okay.
I mean, between 510 to 9 and 510 to the 10.
Well, that's what in some of those young galaxies you can see the clouds like that. Clouds of the CO just sitting there too.
Yeah.
So, all right, I'll talk to you later.
Okay. See you, Judy. I only wanted to say goodbye.
Come on.
Are you going? You're going. I know. So, sorry to see you more.
When are you coming again? Next year?
I'd like to come more often. I'd like to try to come like in. Maybe I'll come in the fall, but my fall has turned into a clusterfuck.
You can always come in the winter.
Yeah, I thought about that.
It's going to be a warm winter. The El Nino is very strong this year.
If you have less snow than we do, I'd like to. The fall is just pretty. I thought I was going to leave nothing in it, and then it just filled up. So, take care. Stay healthy.
I have to
say hi to Kathy.
I will.
So I have to head to an ACES meeting at MIT. You're welcome for old time's sake if you want.
Cool, but
It's hard to say no.
Anyway, good seeing you.
Good seeing you. I'll see you next time.
Yep. So there is some, for the Spitzer IRS, they do take H2 in the vibrational lines for some systems.
Yeah, right. A lot of them.
Yeah, so that just tells you that
There's
warmer
warm
H2.
gas.
Yeah, it
There's
doesn't tell
no-
you the
you
real
don't-
cold H2.
Right. That's it's a few thousand degrees. Yeah, all of these things have
And
H2.
we really need to know the cold stuff. Yes.
Well,
how much cold molecular or atomic there is.
So, again, I'm not a black belt on this stuff, right? I'm just learning that I guess the more complex molecules, like, the carbon stuff, they're the ones that really prefer the cold stuff because they're very
They're down
But
by
they're really
from
thin.
10 to 100.
Well, yeah, and so you're asking for a lot of time to do something
I
that you
looked at
haven't
the numbers for
detected. and-
5044, like HCN.